Okay, so next story, which is very important. So now we come to actually fun stuff. Sign of a permutation. So, so here is an idea which seems a little bit strange at first. So let's consider all permutations. So, definition: a permutation sigma n Sn is called even if it can be presented as an even number of transpositions and odd if it can be presented as an odd number of compositions, of transpositions. Number of transpositions. So this is a beautiful definition, but then you immediately understand that there is something wrong with it. Might it happen that a permutation is simultaneously a product of an even number of transpositions and odd? So maybe it can happen that you can multiply a bunch of transpositions and get, for instance, 3 transpositions. Can that happen? So then this permutation will be on one hand even, on the other odd. And a very deep fact is that it never happens. So every permutation is either a product of odd transpositions or a product of even transpositions. So, so theorem so a permutation cannot be presented as a product of an even number of transpositions and odd number. So this cannot happen simultaneously, and basically even and odd, that's 2 exclusive options. So let me give you an example. Let's start with S3, so S2. With S2 everything is easy. So 1 2 so 1 2, which is just 1 2 goes to 2 1. So this is odd because it's a product of 1 transposition, and the identity one, which is just the identity, so this is even, and you can think of it as either 0 transpositions, or you know that you can write it as 2 transpositions, just say 1 2 squared. So 1 is even, 1 is odd. So in S3 we have 1 2 2 3 1 3. These are odd. And then we have trivial one, and then 2 cycles. 1 2 3 goes to 2 3 1, and 1 2 3 goes to 3 1 2. And these guys are even because if you think about it, this is actually the same as let's see. So first you can send 1 to 3. So now 3 goes to 1, 1 goes to 3, and then 3 2. And this one is actually 3 goes to 2, 2 goes to 3, and then 1 goes to 3. So in this way, you can easily write down this guy says 2 transpositions, this guy says 1, but a priori it's absolutely not obvious. Maybe you can do something and get a product of 3 transpositions equal to a product of 10 transpositions. And the theorem tells you that this never happens. Okay, so we will prove it, and the proof is really interesting. But let me before that give a a way to see whether transposition is even or odd. So that's again this geometric argument, and the idea is that here it's really useful to write your permutation using this beautiful graph we described. So let's, for instance, take this one. So let me take permutation 1, 2, 3, 4, 5 goes 6, say, goes to say 2, 1, 4, 5, 3, 6, and then I have this one, 3, 4, 4, 5, 5, 3, 6 goes to 6. And then, so basically you can count the number of crossings. So crossings are when two arrows intersect. And so sigma is even or odd if and only if number of crossings is even or odd. So this is something which we will see later why this is true, but for now it gives you immediately a beautiful way to compute signs. So just take a permutation, draw it, count the number of crossings, and you get the number. And by the way, here is a wonderful example when you start to see how topology and shapes in the plane and such fun stuff can be related to other mathematical objects like permutations and then to linear algebra. So that's something which actually modern mathematics is full of this kind of interesting diagrams and interesting algebra related to them. So if you will go deeper into mathematics, you will see a lot of nice pictures like that. Anyways, so how to prove that theorem and how to see where this beautiful procedure comes from. So everything comes from another definition of what is a sign, and let me now do that. So this is one which I will use in the proof. So you can ignore it for a second. So definition. So let's take sigma inside Sn. So then a pair Ij is an inversion if I is less than j and sigma of I is bigger than sigma of j. Or, so this is one option, and another option is I is bigger than j and sigma of I is less than sigma of j. So basically, this is when the ordering of your numbers here is different than after sigma. So this is exactly, so if you take this permutation, so you see that pair 1, 2 is an inversion here because 1, 2 goes to 1 and their order is different. Then you know that 3, 5 is an inversion because 3 goes to something which is bigger than where 5 goes. And 4, 5 is also an inversion. And that's it. And actually, the number of crossings is equal to the number of inversions. That's just because two arrows are not crossing when you don't have an inversion and are crossing if you have an inversion. And so now I will define, so definition. And please ignore this definition for a moment. So I define, so if sigma is inside Sn, so I define sine of sigma. So it will be 0 or 1. So this is if sorry, let me do this definition there. So now I will erase this part. Okay, so now let's define. So now I will actually do real definition, real proof, and then I will derive the theorem below. So definition. So let's suppose, sorry, let me adjust a little bit. So let's suppose that sigma is inside Sn, our permutation. So sine of sigma is an element in F2. So this is a little bit weird. So the sine of sigma, I will also denote it S of sigma. S of sigma is equal to 0, or S of sigma is equal to 1. And this is if sigma has an even number of inversions. And this is if sigma has an odd number of inversions. So for instance, for this one, for this one, if this is sigma, then sine of sigma is equal to 1. And this is because it has 3 inversions. So notice that weird thing that a sine is an element of an F2. Why we need that? So of course, if you just want to say that there are 2 sines, 0 and 1, why would you do that? But the reason is we will add them very soon, so this is why I need that. And such guys are called, so sigma, if S of sigma is equal to 0, sigma is called even. And if S of sigma is equal to 1, sigma is called odd. Okay, so now the main important theorem comes into play. So theorem, if you have a pair of permutations inside Sn, then the sine of sigma composed with tau is equal to the sine of sigma plus sine of tau. And here I think of a sine as an element in F2. So basically, you can just write it down, since we know how to add zeros and ones. What it means that if you take even permutation and compose it with even, you get even. If you take even permutation and compose it with odd, you get odd. Odd composed with even, you get odd. And odd composed with odd, you get even. So this is literally what the theorem says. There are no other cases. But of course, it is very convenient to write it down using algebra in F2. And so then from the theorem there is a corollary which we just discussed before. So maybe before proving the theorem I will just derive some corollaries. So okay, so let me derive some corollaries. Let me erase this part. I have some facts. So corollary number 1 is that okay, so let's see. So firstly, S of identity permutation is 0. So and of course this is just because 1, which is 1, 2, 1, 1, 2, 2, and so on, and n has no inversions. Perfect. So another corollary is that now S of sigma inverse is the same as S of sigma. And that's just because if you take S of 1, which equals to 0 in F2, everything modulo 2, it is S of sigma plus S of sigma inverse. And then, of course, we know that S of sigma inverse equals minus S of sigma, but when you do just 0 and 1 arithmetic, it's the same as S of sigma. So that's why this is true. So inverse permutation has the same sign as the original permutation. And then if you take S of a permutation, which is just a transposition ij, of course, this ij transposition, the sign is 1. And the reason is, if you just look at it, so 1, 2, I, j, n goes to 1, 2, j, I, n. And then it's a little bit of a computation to actually see that basically all elements before I and all elements after j will not form any inversion with anything. And here, basically, you just can count these inversions. So I will form an inversion with everything after j, j will form an inversion with everything before I, and then I and j will form an additional inversion which does not go in pairs, basically. So if you count the number of crossings, the picture appears to be symmetric, basically, except this one point. But let me leave it as an exercise. So this is a little exercise. And of course, if you imagine another proof, by the way, is that if you imagine that S of ij is actually equal to 0, then it means that this is even, but then every permutation will be even, because we know that composition of even permutations is even. But then, of course, it has a contradiction. You can just write down any permutation which is not even, and that's easy to do. Perfect. So this is corollary 1. So corollary 2 is that, so if sigma is a product of an even number of transpositions, then this happens if and only if sign of sigma is 0. So basically, even number of transpositions, it's even, otherwise odd. And the proof is very simple, just because if you know that sigma equals to tau 1 and so on tau k, where these guys are transpositions, then of course you just take the sign, and the sign of sigma equals to sign of tau 1 plus and so on plus sum of all signs of tau k, which is just 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 equals to k, which is k. And so k, and as this is of course in F2, so this is basically 0 or 1, and 0 if k is even, and 1 if k is odd. Perfect. So you see, this is a very powerful theorem, and it tells you a lot. So finally, corollary number 3 is that, so number of even permutations is the same as number of odd permutations, and it just equals to n factorial over 2. And we have already seen 3 even, 3 odd for the case of S3, and similarly there will be 12 even, 12 odds for S4, and so on. So why this is true? And this is true because if you take all even permutations inside Sn, and you take all odd permutations, then there is a very simple bijection. But this bijection is funny. So you take a permutation sigma and just multiply it on any transposition, for instance 1, 2. So, of course, a permutation will go to another permutation, and if this was even, this will be odd, because now it's a product of odd number of transpositions. You just added 1. And then why it's a bijection? For instance, because it has an inverse, and the inverse is just take tau and multiply it on 1, 2 once again, because 1, 2 squared is 1. So that's why it is a bijection. And this is very important, so we will see later on how this appears in linear algebra. So, to summarize this part, so there is a very important notion of a sign of a permutation, and there are 2 types of permutations, even and odd, and the main property is that when you compose permutations, signs add according to this modulo 2 arithmetic. Even plus even is even plus odd is odd plus even is odd plus odd is even. And this helps to see that sign of inverse is the same as sign of sigma, and sign of transposition is 1, and so sign of sigma is even if it is a product of even number of transpositions, and odd if it is a product of odd number of transpositions, and these 2 cases cannot happen simultaneously, so only one of them is true. And there was a cool way to compute a sign looking at a diagram, looking at number of intersections, because they are just inversions. So that was it. So now our main goal is to prove this black box theorem that sine of a product is the sum of sines, and it will occupy the rest of the lecture. So let me erase everything. I hope you remember the statement, and I will prove it. The proof is not very hard, but it's pretty interesting. And next lecture we talk about determinants. Okay. So proof. So I need some notation. So let me denote by I of I and j sigma. This number is 0 if pair ij is not an inversion, and 1 if pair ij is an inversion. Okay, so that's the definition, and then of course it's the and I think of it as an element in F2. So that's an element in F2. Fine. So then it's really easy to see that sine of sigma is just sum of these numbers I sigma of ij. Ij, I will denote it as so we know that the sign does not depend on the ordering, so I will look at ij where I look at the pair over all I less than j. Sorry, like this. So I just sum the signs, these numbers I sigma of ij over all pairs. So I is greater or equal than 1, j is lesser or equal than n. So why is that the case? Because, I mean, we need to look at the number of inversions, whether it's even or odd. And then we just look at all possible pairs where inversion might occur, and then we add up once in F2 every time it's odd. Sorry, every time we get an inversion. So of course we get, as a sign, we get a number of inversions modulo 2. So this is obvious. Okay. So then here is a question. So let's look at the following numbers. So let's suppose we have sigma, and let's suppose we have tau. Let's look at numbers I sigma of ij. Okay, so then let's look at numbers I tau sigma of ij. So this tells me what sigma does with I and j. This tells me what sigma tau does with I and j. And let's also look at number I tau of sigma of I, sigma of j. So this tells me what tau does with sigma of I instead. Sorry, let me exchange tau and sigma here. I don't like that. So this will be tau, this will be sigma tau, and this will be sigma. And this will be tau. So what tau does to ij, what sigma does to tau of I tau ij, what sigma tau does with ij. And the question is how they are related. And here is the lemma. And the lemma is very simple. I sigma tau of ij equals to I sigma of tau of I tau of j plus I tau of ij. So this is the statement, and this is very simple but a little bit technical statement. So let's prove it. So the idea is just to look what sigma and tau do to a pair ij. So okay, so let's suppose. So we can suppose without loss of generality that assumes that I is less than j, because we know that this thing does not change. And then there are four cases. So case 1 is tau of I is less than tau of j, and sigma of tau of I is less than sigma of tau of j. So this is one thing which can happen, but also, of course, any of these inequalities can go the other way. So this will be case 2, will be tau of I is less than tau of j, but sigma of tau of I is bigger than sigma of tau of j. Also, part 3 is tau of I is bigger than tau of j, but sigma of tau of I is smaller than sigma of tau of j. And finally, part 4 is when both are bigger. So these are just all 4 logical possibilities what happens with these inequalities. So nothing else can happen in theory just because, 2 inequalities can go in one of these ways. So then let's just look at a table. So let's consider this table. So here I will just write down case 1, 2, 3, 4. And here I will write down these numbers. I sigma of tau of I, tau of j. And then I will write tau of I of tau, tau of I and j. And here I will write I sigma of I j. Sorry, I sigma tau of ij. Okay, and then there are 4 cases, and then it's easy to see what happens. So suppose the first thing happened. So then tau of I is less than tau of j, and it means that for tau, this is not an inversion, so we get 0 here. And sigma of tau of I is less than sigma of tau of j, so for sigma tau, ij is also not an inversion. But then, if you think about this one, you know that sigma sends tau of I, tau of j, so this guy's tau of I is less than tau of j, and sigma also will send them to sigma of tau I is less than sigma of tau of j. So this is also not an inversion. In this case, we see that 0 equals 0 plus 0, so our formula is true. So this is fine. Number 1 case is done. So second case, tau of I is less than tau of j, so this one is an inversion. And then sigma of tau of I is bigger than sigma of tau of j, so it means that, sorry, this is not an inversion. But sigma of tau of I is bigger than sigma of tau of j, so this one is an inversion. And tau of I and tau of j, when you apply sigma, they change the direction, so this is also an inversion. And we get a formula 1 plus 0 equals to 1. So here we have tau of I bigger than tau of j, this is an inversion. Sigma of tau of I is less than sigma of tau of j, this means that this is not an inversion. And then of course tau of I was bigger than tau of j, but sigma exchanges them, so this one is an inversion. And here you have 1 plus 1 equal to 0 equality, which is true because we work with f2. But this exactly is the only case when this happens, and this is in charge of the fact that we don't have the fact that number of inversions is added when you compose multiple permutations. So for the last one we have 1 here, and sigma of tau y, so we have 0, sorry, we have 1 here, we have 1 here, and 0 here, and so still the statement holds. And so this was the end of the proof of the lemma, so the lemma is proven. So just case by case study, we see that this formula holds, and so then we can just compute the sign. So sine of sigma tau, it is just equal to the sum over I less than j, this I sigma tau of ij, which is, and then we know that this is just the sum of this I sigma tau of ij, so it's equal to the sum over I less than j of I tau of ij. So this one is just a sum, the sine of tau, and this is perfect, so this is one of the summands we want. But then we have a weird thing, we have sum over I less than j of I sigma, and here we have tau of I, tau of j. And that looks puzzling because we now have some complicated sum and what it is. But actually, if you think about it, you just add numbers. And you add numbers over all pairs ij. So we know that if we do a permutation, so we can just say that this sum is, of course, since one can just say this, since this thing does not depend on the order, this one is just sum over all pairs ij, where these are just two element subsets inside n times n. Sorry, inside n, just all two element subsets inside n, and then you have this I sigma of tau of I, tau of j. So this we can do just because this function does not depend on the ordering, so it is just a sum over all subsets. But if you just take instead and relabel the subsets, that of course is absolutely the same as summing over all pairs sigma of I, sigma of j, I sigma, sorry, tau of I, tau of j, I sigma of tau of I, tau of j. So the fact is that basically you sum up along the huge set and you can relabel the set by tau. So tau will just relabel all permutations for you, but when you sum up all the values of I sigma, you still get the same thing. And so this one is the same as just sum over all pairs ij of I sigma of ij. And so the thing is just S of sigma. So this is the key part in some sense. Please think it through a little bit. So when you sum over all I less than j, I sigma of tau of I, tau of j, it is the same as to sum over just forget about tau here. Because what tau will do, just relabel all the pairs, and the summation will be still you summing up the same numbers. So in this way, using basically commutativity and associativity of addition, you see that this is S of sigma, and so you get that sine of sigma tau is equal to sine of tau plus sine of sigma. Sorry, so this one is it. And the theorem is proven. So, sorry, where shall I write it? So S of sigma tau is equal to F of sigma plus S of tau. So I hope this proof was transparent, though it's a little bit involved. There are other proofs, there are combinatorial proofs, there are more geometric proofs, there are algebraic proofs, and you can think a little bit about that on your own. So I hope that one day a sign of a permutation will be a subject taught at elementary schools, because it's something kids can understand, you know, this sort of idea that all bijections, all ways to permute objects are divided naturally into types, even in dot, is very fundamental for the entire mathematics. Thank you very much, and next time we will apply all this theory to understand when a matrix is invertible.